Hi ladies, so we are going to keep plugging along with Unit 7. We're actually going to jump past Section 6.2. We're going to cover that tomorrow because that has a lot of application problems. But what we're going to do today is just solving equations. And our equations are called differential equations, which we've already kind of talked about. But specifically, we are going to be solving separable differential equations. So last week we kind of alluded to the fact that differential equations can have a whole variety of solutions, right? And their solutions are equations. Separable differential equations will always kind of follow a pattern in terms of how we solve them and what their solutions end up being. But the process involves getting x and everything related to x on one side, and then everything related to y on the other. Now, if a differential equation is separable, if you can separate your variables, then you can write it where, okay, dy dx is equal to some function with respect to y, what color was that, green, times some function related to x. Now, there are really just two things I wanted to point out with this. Number one, we really like to use the notation of dy over dx. And the reason we do that is because for the time being, we loosely get to let dy and dx be separate algebraic pieces. They're called differentials, so dy and dx separately are called differentials. And what we can do is we kind of move them around, question mark. So if we have this equation, right, where g of y and h of x are just some expressions in terms of y and in terms of x, what we do is that we kind of multiply both sides by dx to get it to cancel, right? And we can do it on the other side. So then we get dy equals, well, some expression with respect to y times some expression with respect to x dx. Well, this g of y, though, whatever it may be, we move to the other side. And so we multiply by 1 over it, whatever it may be, right? And this is just kind of our general pattern in order to get the y and all of its pieces, including its differentials, on one side, and the x and all of its pieces to the other. So it's a little hazy, and it's kind of one of those things where it requires a lot more proof than we are going to put forth, but know that we can do it, and that's the important part. So in example 1, moving right along, we want to give a general solution for the following separable differential equation. Well, first of all, they gave us they gave us y prime, which is no good to us at this moment in time. We want it to be dy over dx. And now what we can do, well, if you'll notice, we can actually cross multiply. Now you could multiply both sides by y, multiply both sides by dx, but what we're doing is we're just cross multiplying. So then we have y dy is equal to 8x dx. Well, now what we do from here, remember you can do whatever you want to an equation as long as you do it to both sides. Well, that even includes taking the antiderivative of both sides. So now those dy's and dx's play an important role, right? Because remember, you can't have an integral sign or an antiderivative sign without the dy or the dx. So we just antidifferentiate both sides, right? So the antiderivative of y with respect to y is y squared times the 1/2 out front, right? Now, technically, there's a plus c. We're going to have lots of c's, so we're going to call that guy c1 for now. And the right-hand side would become 4x squared plus c2, we'll call it. Now, we don't often write the constants on both sides because notice that we can subtract the c1, whatever it may be, from both sides. And then we have 1/2 y squared equals 4x squared. And then some constant minus some other constant is just going to give you some brand new constant, whatever that may be. So we kind of just use this plus c along for the ride. C changes what it is 100 times over, and usually we just kind of say, okay, but it's still going to be a constant. So for us, we need to solve for y now. Now, what we have right now is an expression, right? And it's technically an equation. We just want to explicitly solve for y. So then we're going to multiply both sides by 2 to get rid of that 1/2 out front. So we'll have 8x squared plus, again, some new constant that's still a constant, which is all we really care about. And lastly, we take the positive and negative square root of both sides. 8x squared plus c, all to the 1/2 if you want. Lastly, do not try to split up that square root. I've seen that before. So the square root of a constant, yes, is another constant, but you cannot break up radicals when you're adding in between. So our final answer is just this whole big old expression. In example 2, we are solving the following differential equation, but this time we have an initial condition. We have the point 1,4 that our equation needs to satisfy. So we have dy over dx, thankfully they gave it to us in the right notation, equals the square root of x divided by 2y. Well, again, for this one, we get to cross multiply again. So we'll have 2y dy equals the square root of x dx. And the more that you do this, the more you start to learn to give yourself a little bit of space on the left and the right, well, at the start of each left and right hand side, because our next step is always going to be to take the antiderivative. So the antiderivative of 2y with respect to y is going to be y squared. Again, plus c, but we typically just stick it on the right hand side. And that's equal to, well, this is, remember, really x to the 1/2. So we would want x to the 3/2, and we would need a 2/3 out front. We're just using reverse power rule here. And then we'll throw on this plus c, which is all encompassing. Now, we do need to solve for y, but let's also consider the fact that they gave us a point. It's going to be pretty easy to plug in our point right here, right? Rather than solving for y, which involves square root, which we will eventually have to do, but as we're solving for c, just plug in your point here. Why not? So y is going to be 4. So 4 squared is going to be equal to 2/3 times 1 to the 3/2 plus c. Well, that 1 to the 3/2 just becomes 1, right? So then you just have 2/3 plus c equaling 16. Oops. So then if 16 equals 2/3 plus c, c would be equal to 16 minus 2/3, which would be 15 and 1/3, or let's see, 46 thirds. So we'll plug that back in right here. So y squared equals 2/3 x to the 3/2 plus 46 thirds. And now we'll take the positive and negative square root of both sides. So we have y equals plus or minus the square root of 2/3 x to the 3/2 plus 46 thirds. But let's think about the point they gave us. We only care about the solution of the curve, right? That's what we're finding, an equation, a function that goes through this point. Well, that y coordinate is positive. So if we only care about the one that specifically goes through our curve, or that point, we don't need the positive and negative out front. We only care about our positive curve because the y coordinate they gave us was positive. So we get to erase that plus or minus and call it a day. And then in example 3, we want to solve the following differential equation. Well, again, notice they gave us a y prime. Let's change that to dy dx. And while we're at it, let's go ahead and subtract that xy from both sides. Now it's not going to combine with that 10x, of course, but that's okay. So dy dx equals 10x minus xy. Now, in order for separation of variables to work, remember you need an expression entirely in terms of x and an expression entirely in terms of y. As it's written right now, that 10x minus xy, x is part of both of those. Well, it's good news and bad news. The good news means that we can factor it out. So we are going to have dy over dx equaling x times the expression 10 minus y. And now that thing in parentheses is only in terms of y, and the thing that's being multiplied in front is only in terms of x. So we'll be able to separate our variables from here. So let's see, if we multiply both sides by dx, and notice this time we can't really cross multiply, which is why we're taking the long route this time around. Then we are going to have x dx eventually on the right, as long as we divide both sides by 10 minus y. Now, you'll start to learn that instead of dividing both sides by 10 minus y, we can multiply by the reciprocal. And the reason that that would be beneficial to us is because we're talking antiderivatives. It's easier to see, 1 over an expression times dy times, right? Well, that's going to be the antiderivative of 1 over something. Remember that that's your natural log function. So we take the antiderivatives of both sides, and we get, let's see, the right-hand side's nice and easy. So that's going to be 1/2 x squared, and then we always stick the c on the right-hand side, so there it is. On the left-hand side, well, we have to consider chain rule. We have to do u substitution, or at least do the process, do the steps in our head. So if we know that the derivative of the thing in our denominator is going to be, let's see, a -1, remember you can just throw a -1 wherever you want it, as long as you say, well, I've got 1 over that out front. Now, -1s are nice because you don't need to do 1 over -1, right? You just stick the negative right there. And now you can say, oh, okay, this entire antiderivative is just the natural log of that expression. Of course, in absolute values. And then you've got that minus out front. So we've got the negative natural log of the absolute value of 10 minus y equaling 1/2 x squared plus c. Now from here, our goal is to solve for y. So we are going to need to get that natural log by itself on the other side. So we are going to move that negative all to the other side. So -1/2 x squared. Now again, minus c. Does it matter? No, it's just a different constant, so we can keep that as plus c. And then from here, we can log loop it, remember. So this is really log base e of the absolute value of 10 minus y equaling the other side, right? So we can say e to the -1/2 x squared plus c is going to equal the absolute value of 10 minus y. Now from here, we have a couple other things to consider. Let's work first with that e expression. Now, we almost always end up doing the, let's see, power of a product rule? No, product of powers rule in reverse, where we say, well, this is e to the -1/2 x squared times e to the c, right? Because when you would have that, you end up adding your exponents. So that's what we've got here. The right-hand side will keep in absolute values just for now. But then notice that you've got, some number to another constant. Well, a number to a constant is just going to be, you guessed it, a new constant. So now we have c times e to the -1/2 x squared equaling that absolute value expression. So even though at no point in time, even though we started by adding that constant, we end up multiplying by it. And that's really common when we find our separable differential equations. Now we have to deal with that absolute value. Well, remember that when we solved absolute value equations long ago, we just solved two equations, right? One, so you drop your absolute value bars and you make one, let's see, CE to the, let's call this -x squared over 2. You solve two equations, one where the other side was positive, one where the other side was negative. But we actually just get to keep that plus or minus right there because we're not actually solving, right? We're just trying to find y. So then we subtract 10 from both sides because don't get lost, our ultimate goal is to solve for y. So subtracting 10, we have -10 plus or minus c times e to the -x squared over 2. And that's equal to -y. So the last thing we have to do finally is distribute the divide. So take everything and divide by a -1. Well, when you have plus or minus anyway and you divide by a negative, you're left with a plus or minus. So our final answer is going to be +10 plus or minus c, some constant, times e to that fun exponent of -x squared over 2.